let's get started. I'm a German, therefore punctual person, okay? So I intentionally wrote up the wrong title for today's lecture, okay? Why is this the wrong title? What does this mean? Linear logic and session types. It's an external choice, so you would have to choose, do I talk about linear logic or session types, right? Now, you don't get to choose. Okay? So I could do this. Okay? That means I get to choose the topic of today's lecture. Wouldn't be very useful in the title, right? Why would you put the disjunction in the title if then you talk about one of them? So what you really want, I believe, is this. Linear logic and session types, but both of them, not just one. Okay? So that's now a new connective that we didn't have before, because in the singleton fragment of linear logic, we weren't allowed to have two things. Only one thing on the left, only one thing we could use, and one thing on the right. So we weren't allowed to have two things, so therefore we didn't have such a connective, but now we have it. And so I decided, when thinking over this lecture and some of the questions that came back, that I'm going to actually explain this to you today in two stages. So first I'm going to try to explain the logical meaning of the connectives, the way we usually think about them when we talk about linear logic. And then only as a second step am I going to introduce the concurrent interpretation, the message passing interpretation of the connectives. Okay, so for a while now, we're going to just talk about the linear logic, and then we'll move on to talk about session types. Okay, all right. So what we need to start, we need the new connectives that we can express that two things. We can have both things in our hands while we're trying to prove something. And you remember the judgment we have. The judgment looks like gamma proves A. And this gamma here is a collection of propositions. So it's just like A1, AN. Okay? And when we think about linear logic, the way we think about this, okay, is that these are resources. And this is a goal we're trying to achieve. And we have to use all our resources. And we can use each of them only once. Okay, so that's the idea. So we can't ignore some of these things over here. And if you use it, it's gone. And this is the goal that we're trying to achieve on the right-hand side. Okay, so that's how we have to read the sequent, or that's the way we typically read the sequent. We don't have to. We can also think about these describing the types of channels, and this being a process offering something, but that'll be the second part of the lecture. Okay? All right, so then, for example, let's go back to what the generic rules that don't depend on any particular propositions are. So we have the identity rule. A proves A. Okay, and that just means if I have resource A, I can accomplish goal A. Okay, seems obvious. Important part, this is the only thing on the left. So even though we're in the fully general linear logic with arbitrary gamma, there's only one thing here. If I left something else here, then I would be violating this idea that every resource gets used exactly once, because the other things that are here would be dropped. We're not allowed to do that. Okay? And let's look at cut. It says, okay, gamma 1 proves A, gamma 2 together with A, then with cut, gamma 1, gamma 2 proves C. So the way we think about this in terms of resources is I have some resources, gamma 1, gamma 2, I want to accomplish goal C. I divide up my resources. I use some of them to achieve A. Now I have A. Now I use that together with the remaining resources to achieve my goal C. Okay, so if you think about using these as plans to accomplish something, there is some temporal order here. First you do this and then you do that. But in general, it just means that if you can obtain a resource, then we're allowed to use it. And this sense, if we can use a resource, then we can obtain it, basically. Okay, so those are the generic rules. And then the connectives, the internal, external choice. Okay, let's just write them down briefly because we already talked about them. Let me do the binary form of them. Okay, so A plus B as a goal means we can achieve either A or we can achieve B, that we have to be able to show one of these two things. And then if we have a resource A plus B, and we're trying to achieve C, then this means either A or B, but we don't know which one. Therefore, our plan for achieving C has to account for both possibilities. And so we have to be able to show that, well, if it turns out to be A, we know how to construct a C. And if it turns out to be B, we know how to construct a C. So this is the left rule, and this is the second right rule, and this is the first right rule. Okay? And then cut elimination works the usual way. If you think about this, for example, if you cut this with this, okay, then that you can push up the cut and take this premise and cut it with this here to get the same conclusion. Okay, so we can just examine and see that the crucial step in cut elimination still holds for these rules. Okay, and then we have, so that's the A plus B is the internal choice, and then we have the external choice, which is somehow the dual. So A with B okay, so to show that we can accomplish A with B, we have to show we accomplish A, and we can also accomplish B. Okay, we can do both of them. Which one of those two we actually want is not something we can choose because it might be used somewhere, and wherever it's used, that decision might be made. So here, in the first left rule, we have this resource, and because it's an external choice, we, as we're trying to accomplish C, can make that choice, and here we choose A, and here in the second case, we choose B. So this is the second left rule, and this is the with right rule. Okay, so those are the connectors we already have, and we just generalize them to be n-ary in order to be able to program more nicely, but there's nothing new here. Okay, so next thing is, you want to think about this connective having two things at the same time to accomplish something. Okay, so in that case, we can start with the left rule. Okay, so the left rule would look like this. So we have gamma and we have the resource A together with B while we're trying to prove C. Okay, then what would you expect the premise to say here? Yeah. Gamma A, B, prove C, right? You get them both, which is not the same for this conjunction, which is something called an alternative conjunction, where external choice you have to choose between them. Here you get them both, and those are two very different connectives, right? Just I demonstrated. I want to lecture about this, not the alternative conjunction here. Okay, so in ordinary logic, these two connectives are indistinguishable from each other. Okay, but here in linear logic, they turn out to be very different. Okay. Now we need to construct the right rule for that. Okay, so, and it looks like this. If we have resources gamma 1 and gamma 2, and we're trying to construct A cross B, it means we have to be able to construct both of them or achieve both goals. And if we split up our resources and if you use them exactly once, some of them to accomplish A, and the remaining ones to accomplish B. Okay? And so you can see the difference here. In this right rule, all the resources are copied here, and they're copied also here. And here the resources are being split. So that makes a difference between the connectives. And now we can again look very briefly at how a cut elimination step would work if we introduce it here and then use the left rule here and the two meet. You want to be able to push up the cut to a smaller propositions, while it turns out to be two cuts, right? So first we take this one with this premise here, and we get a proof of gamma together with B gives you C. And then we cut it with this to get gamma 1 and gamma 2 to give C, which is what we want to prove at the conclusion. Okay. So cut elimination still holds, so we have the right rules here. Okay. Then another thing that we get when we have multiple assumptions is a form of implication. Okay. So I'll put that over here. So And this one I read, if I only had the resource A, I could accomplish B. Okay, so it's hypothetical reasoning, okay? And that means that we just add A to our resources, and then our goal becomes B. So if we can prove that, then we can do that, okay? Now we have to think about what that means for the left rule. Okay, so if we have A, B, trying to accomplish C. So the way we think about this is that if we have such a proof, we have a way to transform a resource A, if we have that, into the resource B. Okay? Because here we have a method to take an A and get a B out. Okay, so that means we have to split our resources. We have to devote some of them to show that we can accomplish A. Then intuitively we use this transformation, okay? And that allows us to then use B to prove C, and that's the left rule. Okay, and then we can verify that yes, that works out correctly. If you have a cut between these two, then you can reduce this to a cut from this A with this assumption here. That gives you a proof of B, and then you use this new proof of B and cut it out of here to get your proof of C. So cut reduction, cut elimination still works. Okay. Okay, so this is all well and good. We'll need one more connective later on, but I'm going to postpone that for a while. So this logic is the purely linear fragment of linear logic. And there's one more thing that's introduced, which is that we can replicate resources, but only if there's a certain connective there. So I'm going to, oh no, wait. Sorry, I forgot one other connective. One other nice thing to be able to do is express internally the fact that you're destitute, you have no resources at all, okay? And how do you do that? Well, you say, if I have no resources at all, I can prove 1. So 1 is a notation for having no resources at all, okay? And then, what does the left rule mean? Okay, so the left rule says if I have 1, and I'm trying to accomplish goal C, well, that's just as good as having just gamma, because this represents the empty set of resources. And then see, if you do a cut between this and this, the conclusion is exactly gamma proves C. Okay, because the left-hand side is empty, that's being added to this gamma, the right-hand side is C, so cut elimination works out. Okay, so the one left rule says that resource is not very helpful, let's get rid of it, and the right rule says, well, if you have nothing, then you can conclude 1. Okay.
Is that just a dot in front of the first file?
Yep. That's a dot. So I could just leave it empty, but I want to say, oh, I didn't forget to write it. I actually meant this to be empty. Okay, so that's why I put the dot there. Okay, so these are the connectives of linear logic, with the exception of one thing that will come later, which is bang A, which is often pronounced as of course A. I think that's the way originally pronounced by Girard. Okay, and if you put that in front of formula, you can reuse arbitrarily. Okay, so we'll come back to that. Okay, so with that interpretation under our belt, okay, so now the next order of business is to see what it means operationally if you think about message passing processes. Right? That's what we want to do next. And I'm not sure if I explicitly said this somewhere, but if you interpret these propositions as types, this language is called session types, because it describes interaction along a channel, which is a certain session in which you progress as you go through your interactions. Okay, so therefore it's called, when you progress along this interaction, it's called a session. So these types are called session types long before the connection to linear logic was actually discovered. Okay, it was kind of seen as there's an analogy there, but it wasn't actually discovered that it's actually really truly linear logic until 2010. Okay. Okay, so we already have the computation interpretation of the internal-external choice. So I'm not going to rehash this. Okay, so I want to think about like what does 1 mean in this context? Okay, what does a unit mean? Okay, so actually I'm going to create a table over here. Okay, and we're going to fill that in. Okay, so here we have the type. And here we have the action, And the action is here by the provider. And that means the action that's implied by the right rule for it. Okay? The client would have a matching left rule which does exactly the opposite action in order to match those two things. Okay? And then here we have to put the continuation. So what happens after the interaction has taken place? Okay, so A with B internal choice. Okay, what's the action? That's not by the provider, that's by the client. So the provider sends either pi 1 or pi 2. Right? It sends, okay, so send pi 1 or pi 2, or in general some label from a finite set. And then the continuation is either of type A or type B. If you send pi 1, then the continuation is A. If you send pi 2, continuation is B. Okay? Okay, now what is A with B? Okay, so you receive pi 1 or pi 2. And the continuation again is either of type A or B. By receiving pi 1 over 2 means I branch on what I get. Right? If I get pi 1, I do one branch of my case. If I do pi 2, I do the other branch. Okay? And again, this happens on the provider side, so the client makes a complementary action. Okay, so receive pi 1 and branch on it. Okay, so now we want to think about what 1 could possibly mean. Okay, so I don't know if you can form a conjecture on that. So let's start on the right-hand side, okay, with the second rule there, the left rule. By the way, you notice that I always write the left rules on the right and the right rules on the left, okay. Why do I do that? Because I want to think about if these two things match up, I need to put a cut between them, okay. And to put a cut between them, I need to write the right rule on the left and the left rule on the right, okay. Okay, so, all right, so if I think about the situation here with a context gamma and I have a channel x colon 1, okay, and I have some process over here that provides along some channel z on the right-hand side, okay, then, so this is the general schema of these things, by the way. I'm going to have some process here, and because it's a left rule, we don't interact on the right, so the right stays the same. And this is still called the 1 left rule, okay? And what I have in the premise usually is a continuation of what happens in the, because I interact along this channel, and then I continue, and the continuation is what's usually in the premise, right? Okay, so I'm going to do something, and then I'll continue with P, okay? So even without really thinking, when I'm looking at these different things and what they mean operationally, I get this far, right? I only have to worry about what do I put in here. Okay. So the salient feature here is that the channel X exists before the interaction, and it's gone after the interaction. No longer here for P. So this interaction corresponds to closing the channel, terminating this channel of communication, right? Because it's no longer there. Every channel is provided by something. If the channel is gone, the provider of it is gone, right? Okay. So what we're doing here is we wait on X. I'm reminded of the streetlights here. They always tell you wait, wait. Okay, here you only have to say it once instead of 5 times, okay? So you wait for X, which means you wait for this computation of this process that provides this service here to terminate, and then you continue with P. And then the corresponding right rule, well, if we have nothing in our context, okay, and here along X, we have 1, and there's no premise, then the obvious counterpart is we terminate, or rewriting it as closing, we're closing this channel. Okay? And then again, without much thinking, we can write the operational rule. It looks like this. If we're, which is in parallel with on the channel C and continues at P, what does it become? Just P, right? Because this process terminates. I'll put parentheses around here. This process terminates, and this one continues at P. Okay? Completely logical. All right. Over here, so then the type 1, from the point of view of the provider, which is the right-hand side, it basically has to send some token and saying that I'm closing the channel, so we'll just say close channel. And there is no continuation, okay, for the provider because, well, I'm done when I'm closing the channel, I terminate, okay? Okay, so an interesting observation here is that if I had generalized singleton logic just very slightly and said the left-hand side can either be one thing or nothing, okay? We call that sub-singleton logic, basically singleton, but the left-hand side can be empty. Then the one connective exists in that logic, okay? That's a good news because then processes can terminate by other things than just forwarding, okay? And so the implementation that we build is actually for sub-singleton logic. So we have that connective one in there, and you can write processes that have nothing on the left, okay? It's a little bit nicer than always having like an alpha on the left-hand side. Okay, so that was one. And so this is kind of not very controversial, but weirdly enough, in our original paper in 2010, when we proposed this, we actually did it differently, okay? But one is always smarter a few years later, okay? It's obvious now, right? Well, how could we have done it differently? But okay. So now the next thing is maybe let's look at linear implication, okay? Lolly. So functionally, you think of A arrow B as a function that takes an argument of type E and A and gives you a result of type B, okay? So here we have something fairly similar. Okay. So we have gamma proves, and here we have a channel X of type A. So this means A linearly implies B, but it's often pronounced A lolly B because it's a lollipop on the side, okay? So A lolly B or A linearly implies B, okay? And, okay, so what can we say about the premise? Well, in the premise we have a new assumption. The new assumption is some Y, we don't know what name, okay? Y colon A. And on the right-hand side, well, this is a communication along the channel X. So the continuation, there's only one possibility the continuation needs to be B, okay? So what could possibly actually be here? It can only be something that receives a channel and then continues as B. And the channel that we received has to have type A. So it's just like a function getting an argument, but here, along this channel X, we're being sent another channel, and this other channel that we're getting has type A. So in singleton logic, we didn't have the opportunity to pass channels along channels. Because just having one thing on each side, we can't pass that away because then it'll be gone and we'll violate our invariant of having just one thing on each side. But here now we can pass channel along channels. So originally we designed this, this calculus, the assignment of process terms as something where the process terms are expressed in the pi calculus, okay? And the pi calculus has the characteristic that you can pass channels along channels. So it was a good match for that, okay? All right, so here we don't use pi calculus syntax anymore because it's nice to talk about abstractly, but it's very hard to program with. And so, okay, so what we do is we receive a y along x, receive along x of y, and we continue with p, and that's p. So that's all it is, and we know that P can depend on Y, so maybe we should write P depends on Y just to be clear about that. Okay? And that's, of course, we can see that it depends on Y. Okay? We receive the channel. In fact, now we have to use it, right? Because every channel we actually have to use in some form or other. Okay, so now the tricky part is what is the left rule? Okay? So I'm going to actually do some violence to this left rule. Okay? Because I want to write programs in the second part of the lecture. And if I put this rule, then it's going to be at odds with what we can actually use in programming. And I'll try to motivate it why. But the left rule, the changed left rule would be like this. It'll be like gamma y colon a, x colon a arrow b. And on the right-hand side, I'm going to have z colon c. And then in the premise, I'm going to have gamma x colon b. And I'm still going to have z colon c over here that doesn't change. Okay? So rather than saying that I have to devote some resources to prove A, and then you continue with B, I'm going to say that that resource has to already be there. Okay? So logically, in terms of inference, those two are equivalent. If I have this rule, forgetting about the channels, or if I have this rule, the logical consequences are the same. Okay? And that's because you can interderive these two rules from each other. Okay? But, and this is a big but, if you take this as your definition of the left rule instead of this one, then cut elimination will fail for you. Okay? And in one of my lecture notes, I have some examples of that. So this is a weird left rule. Okay? And it's really not sufficient to get cut elimination, even though it's logically equivalent to that if we have cut. Okay? So that was a real puzzle to us for a while, but eventually we figured out that there's a way to recover. Yeah?
You intentionally use the same tests in the overall on the right? That's something
Yes, I intentionally use the same, and the reason is this. Here the x stays the same on the right-hand side. So if I have an interaction, which I'll show you in a second, we need to make sure that after this interaction takes place, this x is hooked up with this x. So this name stays the same. Okay. Again, there's other ways to formulate the system, but this is most closely related to the way that you write the programs. But it's an excellent question. We were wondering about this for a long time too, when we're writing the system. Okay, but what does this process term actually have to do? Well, based on everything I've said so far, you should see what it does. It sends y along x, right? And when you do that, then the channel now suddenly has type B because you have satisfied the first part of the protocol, which says send an A and continuous B. So we just send along x the y, and we continue as q, and this is just q. Okay. If you take the original rule, the construct is a lot more complicated, which is why we wanted to simplify it. But like I said, there's a deeper logical justification for it, but I don't want to get into it. Okay? Are we okay with this? Okay? And cut elimination, well, we know that it fails. Okay? But this particular interaction actually does work. So locally it works, even though globally there's a problem. And what you do is, what do? You have to do a cut of this with this because they have the right types to be cut. And you have this. What happens to the y colon A? I think you have to somehow substitute the one y for this other one, but I can't quite see it right now. Okay, but the computation rule I can write down for you, and you should be able to write this down too. If you have one process that receives, y is you receive along channel C and continue as P depending on y, and you put this in parallel with the process that sends along C the channel D. after the interaction, what should we have? Well, we should still have two processes, right? Because both of these sides have a continuation. This is going to be a P here and a Q here, except that this isn't the original P, but
Depends on
yeah, we have to substitute the channel that we actually send, which is D, for the variable y in P. So we substitute, I'll write it explicitly, D for y in P sub y. Okay? So we have communicated the channel from here to over there. Okay? So that's the goal of that particular operation. Okay, so to fill out our table here, A linearly entails B means that from the provider's perspective, we receive a channel and we continue with type B. Simple enough? Okay. Yeah? Is there a question? Okay. So I've just not one connective where I haven't done yet, but just the tensor or the simultaneous conjunction. Okay. And what would that actually be? Okay. So if I look at this right rule here, okay, then actually, let me start with the left rule in this case. Okay. All right. So how does the left rule work? So I have a gamma, and I have an x of type A tensor B, and on the right, I have a z colon c. By the way, if you ever try to do this yourself, this is a really good technique. You know, you never either read or write these rules like, you know, left to right here and then left to right here, unless you already know exactly what you're doing, which you almost, well, okay, I almost never do. Okay. So the way you do it is you always start at the bottom, well, almost always, and you fill in the pieces with what you already know, what's obvious, what really has to be there, right? And you don't try to speculate about this. That's just, okay, let's figure out what we know. And eventually, you have a few gaps left and you can fill those in, right? All right, so we have a gamma here, so that doesn't really change. And we have an A, and we may not know what to label it with. And we have a B, we may not know what to label it with. And we have a turnstile, okay, from this left rule there. And because we interact on the left, the right-hand side stays the same, right? So this will be the left rule for tensor. Okay. Okay, so now, by analogy with everything we have done so far, if we have A tensor B, then we somehow should interact according to A and continue as B. Because we have read all the connectors from left to right. It isn't really forced, but it's nice to do it that way. Okay, so that means if the continuation turns out to be this is going to be the same x. Okay, and you have a new y here. You don't have a name for that, you have a new y. So now can you speculate on what the operation here might be? Yeah? Maybe you can see it that way, but there's a simpler operation interpretation. So in the premise we have a new y. Where could it come from? We receive it along x. It's the only channel we actually single out. So where else could it come from? It can't come from z. The only place where it comes from is from x. Okay. So we receive from x the y, and this is going to be our okay. And then the channel x changes type. It goes to B because we have received our channel of type A, which we call y, as we continue with P. Make sense? It's a little weird, right? The slightly weird thing about this is that this looks extremely symmetric, right? Two things. But there's a slight asymmetry that we decide, okay, we're going to receive y and continue with b. Now, we could equally well have said we receive a channel of type b and continue as a. But then when you actually read a type in your program, you read, then you have to jump, and then you read backwards and so on. You don't want to do that. So we read it from left to right. Okay. Now, in a functional language, you think, oh, the pair is completely symmetric, but it's actually not, right? Because you have a pair, mn, you evaluate m first, and then you evaluate n. So it's not symmetric either in the same way, right? There is some order in which you actually work with these things. And the order here is represented in the fact that you receive one channel, and then you continue evolving the type of the channel with the other type. Okay, so now that under our belt, let's write the right rule, okay? So we would expect it to be this, but for the same reason for Lalia, I'm going to give you a different one. The different one is going to send just a channel, okay? So, because we wanted to match the receiving of a channel exactly, okay? So, okay. So the tensor right rule, which is weird because it has just one premise, but it looks like this. Hopefully I can figure it out. So on the right-hand side, we have x of type A tensor B, right? That's the channel that we're communicating along. And on the left-hand side, we have gamma, okay? And then afterwards, x, the channel x has to be of type B, okay? And we have some turnstile here, some turnstile here. Presumably gamma survives, okay? So gamma is still here. So that's how much we know. Now, from the thing over there, the next thing we're hypothesizing, we're sending a channel along the channel. So I send along x the channel y, and I continue as, well, let me call this q, okay? So this should be just the continuation q. So now you have to worry, where does the y come from, right? And over here, what we're saying is, we devote some of our resources to construct that channel y, okay, or the proof of A, I should say. And here, we're requiring it to be already present. And then when we send it, it's gone. Because everything is linear, we have actually sent it over there to that process. So now it has disappeared, so we no longer have it, okay, which is this. So again, these two rules are interderivable. This rule violates cut elimination. If you think about it naively, but you can recover from it. So it's a special type of rule. And so if you now look at all the rules, you see that these rules have just one premise. And that's nice because we have a single continuation in our program instead of two continuations. And so then if you look at the type over here, a tensor B, it means you send a channel of type A. In both of these cases, the channel has type A. And you continue as B, okay? So there's a very strong symmetry here, right, between internal and external choice and between receiving and sending a channel. If you do classical linear logic, that symmetry is expressed a little bit differently from this intuitionistic case, but the same symmetries are present, of course. It doesn't really change the essence of things. Okay, so that's the whole system of session types, enough for us to write some interesting programs. But I want to pause here. The operational interpretation, okay? We have to match a process that sends a channel along a channel with one that receives, okay? But the good news is we already have that rule here. So that same rule will work. We don't need to write a second rule, okay? Because you just change the role of who sends and who receives, but the rule is the same in this formulation, okay? Okay. Okay, these are not going to survive for very long, so you should look at these rules and ask me if you have questions. Yep?
So with the tensor version, the operational semantics of the tensor is just the order change, right?
Yeah, actually I should have said, and this, thank you for pointing this out, this connective here is now commutative. Because you communicate along channels, so these channels now give you the connection between the two, so it doesn't matter where they are in your configuration. So previously you communicated either with your immediate left neighbor or immediate right neighbor, so it was very important that the vertical bar was not commutative. But now it's commutative and associative, so where these things are in your configuration doesn't matter. So this is kind of like an abbreviated way to write the rule. And yeah, in principle, they can be very far apart. And so it's just a matter of which one of these two provides the service and which one uses it, how to read the rule. Yeah?
Is there a counterpart for one?
Yes, there's a counterpart for one, which is called bottom. What that basically means is that if you look at the one rule up there, here, you flip this over, you have bottom here and the empty context here. It means that you no longer have any client. Okay? So the right rule will detach you from any possible client. And so that means basically, well, I think there's such a construct in Unix C where you can just like a process and detach it so it runs like by itself. Okay? In this system, if you do that, then you can never ever interact with this process by itself, right? But then you're in a situation where, like, if a tree falls in the forest and nobody's around to hear it, does it still really fall or not? Okay? So you can write down the formal rules, but it's not really clear that it means very much. Okay? But for reasons of symmetry, it should absolutely be there, and it's there, but yeah. So probably like next month somebody finds a really good use, and then we'll just kick ourselves that we didn't have it. Okay? That's the way it always is. But it should absolutely be there. There other questions? Yep.
So even though parallel composition is now commutative,
Yeah.
we still maintain the distinction where the provider is the right rule and the client's the left rule.
That's right.
Okay.
Yeah. Okay.
So in deriving, do you remember the dash dot symbol again?
Which symbol?
Like the dash symbol.
This. You mean? Oh, linear implication, also known as lolly. Yeah.
So it seems like when we were deriving these rules of the lolly, we ascribed some meaning to not just receiving a channel, but also sending a channel, right? That's the lolly L.
Yeah.
But then separately, if you say we need the time, we need the tensor term to describe what the action of sending a channel. But like it seems like we already have a means to send a channel having bond. It's like do we need the tensor thing in order to make it possible to send a channel? It means like we already have a means to send a channel. What exactly is the relationship?
Right. So you have to make a fundamental choice if you want to express the symmetry that's inherent in all of this by a left-right symmetry the way we do here, or by being able to say you can a tensor B can communicate with a lolly B and vice versa. And if you take the latter choice, then you only need one of these to connect. Well, you need half as many rules, okay? Because you abandon the left-right distinction, then everything lives on the left. And that's the approach for classical linear logic. So it cuts down the number of connections in half, and you have an operator that takes the opposite of a given type, okay? And then you can communicate along a channel if the types of the endpoints are opposites, okay? The problem with that is that if you try to do this and build a programming language on top of that, it doesn't fit very well in the function programming. We have a function that returns a value. So, and there's other issues, like if you want to have a dependently typed version of this, or you want to layer other things like temporal logic on top of this, it gets very difficult because now you're working in a classical logic rather than an intuitionistic one. So, my experience has been that it just fits much more nicely in the whole ecosystem of what you want to do with the programming language. If you have this slight asymmetry between left and right, and that means you have twice as many rules as maybe you can get away with, but you don't need to dualize. I think experience with functional languages bears this out because you always say we pass an argument to a function. You don't say I pass a negated argument to my continuation. I mean, people don't do that, okay? Maybe once in a while they might be a useful programming thing, but in general you don't do that, right? So, and the nice thing about that, I think the real reason is that you say, well, if I have A, arrow B, and the argument is type A, you only really need to talk about A. If you want to say, if I have A perp tensor B, and I have A, then you need to talk about A and its negation. So if you define a type like expressions or a type like list, right, you can't just do that. You also have to talk about the opposite list, okay, in your programs in order to write programs now. It's I don't know. I found it easier to just work with something that's very analogous to this instead of having to work with this, even though at a formal level, it might be a little bit more parsimonious. But this is an excellent question, and we wrestle a lot with that particular issue. Other questions? Okay, so now I want to fill this with a little more meaning to actually write some programs. And of course, we start by writing types, right? And then we write some programs. And I want to do object-oriented programming today. Okay, this is on tape, okay? Which, I think this is the first time I've ever said this, okay? But here it is. Okay, so I want to describe the interface to a data structure that's implemented as an object which is a queue, okay? So I want to say a queue with elements of type A. Okay, so it behaves like an object, so it receives messages, and you can do two things to a queue in my implementation. You can insert something at the end, enqueue, or you can dequeue something from the front. That's the only operations I have, okay? Now, should there be an internal or an external choice? External, right? Okay? Okay, so if you just walk away from these 4 lectures and understanding the difference between internal and external choice, okay, that's already success, okay? So it's an external choice between an enqueue and a dequeue. Okay. So next we have to figure out what should happen if the server receives an enqueue command. What's the next thing that has to happen? Yeah, you want to put something to the queue, so how do I express this as a type? What does the client have to do? Yeah, the provider has to receive a channel of type A, right? Because the channels are the things that are being stored in the queue, which means that the client has to send a channel of type A. And what type construct is that here? You only have 2 choices, right? It's lolly or tensor. Which one? Okay. Who thinks it's lolly? Okay. Who thinks it's tensor? Who has no clue whatsoever? Okay. All right. Okay. It's lolly. Because we're writing this type from the perspective of the provider. And if you look over there, okay, you see that the provider receives a channel of type A. Right? We want to put that into the queue because we're providing the data structure as a service, right? And then it behaves again like a queue. All right, if we receive a dequeue, what do we do? Okay? So ideally, you want to give back the element, but we can't do that in all cases because the queue might be empty. So what do we do next? Yeah?
Could it be like the tensor product? The thing that we're like sending is an internal choice between like nothing in an element, and then the thing that's going to happen next is a queue, another queue.
Yeah, you could do that, but I think I would flip this.
Yeah.
Okay? So we make it an internal choice. So we respond by one of two labels. We say, okay, none, there's nothing in the queue. Or we say some, which says, yeah, there is something in the queue. That's an internal choice because as the provider of the queue, I know whether I have something in there or not. So I'm going to send back none or I'm going to send back some, right? Makes sense it's an internal choice? Because the provider of the service knows. Now, if it's some, there is something in the queue, what should happen next? Now we send the thing which is in the queue, which becomes tensor, right? Because we send a channel, and then we behave again like a queue. Okay? Now, the last thing that's remaining is there's nothing in the queue, and I try to dequeue. There's two choices. I could either just circle back and still be a queue. So my client could still do something with it. But then I could never actually finish interacting with the queue. The queue would be around forever because it's linear, and I would be. So another choice, which I found often very useful in this kind of data structures, if you're trying to dequeue, there's nothing in it, you actually terminate. Okay? So if you want to deallocate a queue, you remove all the elements from it, and at the end it just disappears because it closes the channel and terminates. So it's a convenient way to program. It's not forced, but another way to do it is to circle back and have another thing that says deallocate yourself. Okay. This is a nicer way to do it. Okay, so that's our type of queues. It's a session type because you have, as a client of a queue, okay, you have a session with the queue, and then you send these messages, NQ, then an X, NQX, maybe DQ. If there's something in it, you get the element back, and so on. Does that all make sense? Now, an interesting property, yeah? Oh no, what happens when the client receives the one, so the client has to be ready for both choices because it's an internal choice. And in the branch for one, it waits for the queue to terminate. In the branch for some, it then receives. Was there another question back there? Yeah? Okay, so if you put QA here, then the queue will continue to exist, right? And so that you can now NQ new things and you can DQ more things. But because there's no other part of the interface, once you allocate a queue, it's going to be there like forever. Right? It can never terminate because on every sequence of interaction, you recurse back to be a queue. So it's going to be around forever. If you want to be able to terminate the queue, finish it, you either need to say I have another thing that's here, deallocate the queue. Okay, that's tricky. Or you just say, well, if I try to dequeue something from the empty queue, well, the queue is not very useful. It's empty at that point. We'll just have it terminate. So deallocating the queue is built into the communication interface. Again, it's not forced to do it that way. It just turns out it's a convenient way to do it. Yeah?
This queue used for buffering?
No, this is just, it could be, but this is just used for a little programming exercise to illustrate the types that are on the board. Yeah.
You said that DQ was tricky, but I don't see why.
Well, now that we have it on the board, it's no longer tricky. Now it's obvious. Okay. If you add a terminate at the end here, right, or deallocate the queue, I can't say this. Why can't I say this? Because there are things in the queue of type A which are linear, so I can't just terminate the queue at this point, right? So I won't, if this is my specification, I won't be able to give an implementation, really. Okay, so that's why deallocation is tricky. That's why it's easier to say, well, if I'm trying to dequeue and happens to be already empty, let's take the opportunity and terminate. Okay. Yeah, linearity, you have to be careful about linearity. Yep. It's the same. Whenever you are at this particular point, The only additional information you have is there's nothing in the queue. And so you can't terminate. If you say down here, you don't have that knowledge. Okay, so I want to write now the implementation of this. So are we okay with the type? Okay, good. By the way, how do you specify a stack? Same thing, right? Implementation is different, but the type should be the same. Probably wouldn't call this enqueue, right? You probably call this push and this pop, right? But otherwise, it's the same. In fact, there is a little theorem that actually took a long time to figure out how to prove, is that because of linearity, the only implementation of this is if you enqueue a bunch of things and then you dequeue a bunch of things, one is a permutation of the other. Okay? It seems like an obvious property, but it's actually hard to prove. So we needed to actually develop a little bit of a theory of logical relations to figure out, and then a kind of a, well, it was not trivial. Okay, even though it seems like an obvious property. Okay, so in the functional language, you get these theorems for free by parametricity. I don't know if you know about this kind of thing. If you do, this A here is important, it's nice, it helps you, but you get much more information out of the fact that these types are linear. Yeah, did you have a question?
I was just going to ask, like, why, like, because that's why it was hard.
Because it's very hard to reason syntactically in a situation where you have a fairly rich type system and you have recursion. And so you need some kind of step index logical relation in order to prove that, at least as far as I know. Yeah. Okay, let's spend most of the rest of the time programming, because I want this. I said in the previous lecture I strive for failure, but now I actually want to succeed. Okay. So the way I'm going to implement it, I'm going to draw a picture somewhere. Or maybe I can get rid of the logical rules, because these exist in the literature and probably in somebody's notes, right? So I probably can get rid of them here. So the way I want to implement this is completely in an object-oriented style. So not the way I did the counter, but fairly similar, okay, at some level. So what I want to do is the following. I have a bunch of processes which are connected. And the last one doesn't have anything here. So they execute slightly different programs, these processes. And this little circle means I'm providing that service and I'm using these. So I'm providing along this channel, okay, the service of a queue with elements of type A, okay? And so I'm also holding an element, which is the first thing in the queue. And yeah, some process is providing that, some data structure, who knows, okay? And this here is going to hold x2, this is going to hold x3, and the last one is empty, it doesn't hold anything, okay? And these interfaces here all have the same type. Each of these channels, everything from here is a queue, everything from here is a queue, and from here it's an empty queue. Okay, does that implementation idea make sense? It's like every node in the queue is actually like an object, refers to another object, refers to another object, except objects here are processes, right? Okay. Okay, so now I need to write two different processes. One called empty, and one called element. Okay? Because this one has a different type from this one. Okay? Okay, so let's write the element process first. Okay, and when we write it, you want to think about what the type of it is. Okay, so what is the type of element? By the way, it's completely hopeless in my experience even though I designed this language, I'm probably the person who's written the most programs in it, to write anything without writing the type first. Because even more complicated than in a functional language is the fact that whenever you have an interaction, the type of what you're doing, the type of your channel changes. So when you do a functional program, you're used to the fact, well, this is a function from int to int. It's always going to be a function from int to int. That's it. But here, it starts out as a type q. Once you receive a message, suddenly the channel has a different type. So unless you're always aware of the type, you're not going to get the program right. At least that's my experience. So what is the type of element? Okay, it's a process offering that some type q of a. So that's easy, right? It's on the right-hand side because we're providing the q service to the outside. And what does it depend on the left-hand side? Yeah, so empty is a different process, so it's another element process, and what is the type of the element process we plug in there? It's again a Q, right? So we have a T, which is the tail of the Q, which is also of type Q. And so hopefully empty here will also provide E colon Q, so we can plug it into that port, basically. But there's one other thing we also have to depend on. X of type A, right? Because you see here, we have to keep a hold of the element, right? This is why we couldn't do this in singleton logic, right? The linear line we could have done, it kind of did, but we can't hold any elements. So Q is pretty useless unless it can hold elements in it, okay? All right, so now we should be able to write this program. Okay, so Q is implemented by element, which owns the tail of the Q and the element X. Okay. Okay, so how do we start? We look at the type. So in an object-oriented side, what happens is we almost always answer a request from the outside world. Right? We receive a message and then we do some computation, return the result, right? That's how it works. This is an external choice. So the first thing is we do which message is being sent to us. It doesn't pay off to look into this queue or try to look into this element. We own them, but what would we do with that information, right? Okay, so we'll start with a case on Q, what we receive along Q. And there's two possibilities. We can receive an insert, or we can receive a delete. Okay? Oh, yeah, sorry. Receive an NQ, or can we receive a DQ? Okay, let's write down what the type is. Okay? At this point in time, we have to write a process which has the following type. So we still have X colon A in our context. We haven't touched T, so T is still a Q. And what's the type of the right-hand side? Look at the type over there. Yeah, so it's Q of type A, lolly Q. Does that make sense? We've gotten to this point because we received an NQ, so the continuation type is this type. Okay, so now we have to program against this type. So what's the next thing that we do here? We could receive the A, right? That would make sense. Okay, so we say Y is what we receive along Q. Okay? And now what is the type after that? So we have X colon A, we have Y colon A, we have T colon Q that hasn't changed, and the right-hand side has type Q now. Right? Because we have received the A, so the continuation is we're back at Q. Okay? All right, so we hold the X and the Y. Okay, so now actually we have to think about the algorithm. All right, what's the algorithm? If you get an element being passed into this queue, okay, yeah? Yeah, so this would be T. So the algorithm is to do a bucket brigade and pass it back here, okay, and then we get to the empty queue, we add a new element here at the end, right? And then, so n-queuing is rather expensive, but a lot of things can happen in parallel, right? Okay. And then dequeuing should be quick because it happens at the beginning of it, right? Okay, so how do we send it to the back? Well, how do we send it to the back? We say we want to insert into T, so we said send along channel T the insert message, and then send along T the channel Y. Okay, does that make sense? Oh, okay. NQ. We send the NQ message and then we send the Y. Does that type check? Okay, so now we're the client. This is an external choice. So we have to send one of these two labels. So we send this label with the NQ. We're the client. Now it has this type. We have to send an A, and fortunately Y has type A. Right, so we did the right thing. After we do this, what is the type? Well, we still have X colon A. And the right-hand side we haven't touched yet, so that's, we haven't touched again, so that's still of Q. But what's the type of T? Okay, so we have to look at this. We send it the NQ message, so then the type became that, and then we send it the element, and the type became that. Okay, so the type of it is T is now again Q. Okay, and this is very good because that allows us to make a recursive call, right? So now we have NQ'd that element, we have moved it on down the bucket brigade, and now we're ready to accept the next element. So we just say, okay, Q is now implemented by element, passing it the same T that we started with and the same X. Okay, this code makes sense? Of course, you don't know the syntax, but I know the syntax, so it makes sense. Okay. And we have to type check it, but basically we trace what the type checker has to do over here, and it works. Okay. Now the nice thing is there is a lot of concurrency here in the sense that these two things happen, like are being absorbed on the left, and we can accept the next command while the thing is in flight. If the queue is long, that could be a long time, but we don't have to wait for it to arrive at the end, right? So when we reason about the parallel complexity of this, it looks rather good. Even though the total amount of work that you have to do is quadratic in the number of elements that you put into the queue. But the reactivity, the reaction time between two different operations is constant, which is nice. Okay? Okay, now dequeue. How do we dequeue an element? So the first thing we have to do is, if you look at the type over here, we have to tell our client whether we have something in the queue or not. What do we tell our client? We have something, right? Because we have X. So it's unambiguous. So we tell the client Q and respond, yes, we have something. We send the label sum back. Okay? All right, so that's good. So now what is the type here? We still have X colon A. T is a Q. And what's the type of Q now? A tensor Q. So what does it mean we have to do here is to send an element of type A, right? Tensor means we send an element of type A, behave again like the continuation Q. Which element do we send? We hold the element X. So excellent, so we can send that. So we send along Q the element X. Now what is the type at this point? X has type, oh no, X is gone, we no longer have it, we have sent it. T is a Q. And Q is also of type Q. Okay, so what do we do now? Yeah, so one answer that was proposed here we forward, and the other one we request an element from Q. So those are both from T. So both of them are viable, right? In the one case, we move all the elements forward by one, right? That could take a long time. Is after we have sent out this element, here we move that, we'll just say all further requests along Q should actually go to T, which is the tail of the queue. Right? And we should just terminate. No reason to stick around. So that's the more elegant way to do it. We say from now on Q is implemented by T. And it works because both of them have the same type, so we're allowed to do that. So that's just forwarding. Okay. Okay, so that's our code here. Makes sense? All right, so I think I have enough time left to show you the codes for empty also, or actually for us to program it together. What's the type of empty? Well, empty has nothing on the left-hand side, and it has type Q on the right-hand side. Right? It has nothing here. It doesn't hold an element. It has no further things coming. The back, it just marks the end. Okay? So now we have to program that. Okay, so Q is provided by empty equals, well, as before, we start with a case because we need to see whether we want to process an NQ or a DQ. If we get an NQ, what do we want to do? NQ something to the empty Q. Okay, we have to receive the element. So X is what you receive along Q. Okay, so now we've interacted with Q and its type has gone back to the type of the Q, right? It has circled around once. Okay, and we now hold X. What do we do next? We want to start an element process, right, that holds that element that we receive. So we want to start an element process. We want to say, okay, the Q is now implemented by an element process, and we're providing it with something I don't know and X. Right? So this element process should get X. Right? But I have to also provide it with a Q. Where does it come from? Empty, but we don't have empty because that's us. So we have to start a new empty process and then pass that into here. Okay? Okay, so we start a new empty process E, and we pass that into the element process together with the element X, and further interactions now along Q go to this element process. Okay, if we're supposed to DQ, what do we do? We have to respond with what? Either the label none or the label some. None, because we don't hold an element, so we say Q.none. Okay, and after we have sent that, what do we do? What's the type now? So we terminate, so we just close the channel, close Q. And that's it. Okay, so the complete implementation of this highly efficient queue, okay, is now on the board, okay? So this is fairly typical how you program with this kind of thing, right? It's just that this particular piece of code has almost all, or maybe all the connectors we have discussed in it, right? Okay, so I'm starting to run out of time, so I do want to talk a little bit about what's ongoing in terms of research on this kind of thing. Since I don't have time to really talk more about this. Okay, so the first thing I wanted to mention is that linear logic also has bang of A, like we talked about, or of course A, which can replicate A. And so in the original paper, we put that in there, and we figured out how to deal with that. So basically something of type, of course A is something like a server that can be replicated, okay? And we later discovered that it's best to decompose this. So we actually, what we do is that we think of all the types of being indexed by whether they're linear or not. So at the linear layer, you have AL, arrow, BL, and all the other things, okay? But then you also have a layer which things can be replicated or copied or dropped even. We call it AU for unrestricted, okay? And then you have a way to embed, to come down from something unrestricted to be linear. And here you have a way to go up from something linear to make it unrestricted, okay? And then the usual bang A of linear logic is just the composition of those two shifts. So it's a downshift of an upshift of a linear A. Okay, so this would be linear. And if you do that, then you get a lot of very nice properties of the calculus that don't have if you take this as your primitive. It's nicer to program with. These two things form what's called an adjunction, okay, if you know anything about that. The judgments we have generalize in a very nice way. But more importantly than all of that, what you can do at this point is you can populate this unrestricted layer with other things. So we can add here, for example, AU arrow BU, or we can add ordinary products, and so on. And so we can actually now combine our ordinary linear language with message passing semantics with a functional language up here, okay, and stay within a logic. So in fact, this formulation of these two layers going back and forth are due to Benton 1995, I think. We give a novel semantics to that, but the idea has already been around long before we started our work. And that gives us a very nice integration of a functional programming language with a message passing language. And the logic here is intuitionistic logic, and the logic here is intuitionistic linear logic. Okay. And I can't go into the details, but you can look it up in some of the papers. Okay. And we can recover the fact that certain things can be replicated. Okay. So then some of the things that are going on, I'm probably going to look at my cheat sheet here, make sure I'm not forgetting something. Okay, so one of the things I've been working on is a shared memory semantics for this. And so the natural semantics that goes with the sequence calculus here is one of message passing. But if you look at it a certain way, you can also read off a kind of shared memory semantics for the same thing. And I wish that we had taken that path originally, because then the implementation would have been nicer. But we just did the implementation seat of the pants. But what I'd really like to do is take the message passing semantics, and if you happen to know that all of the things run on the same machine, implement it by using this shared memory semantics. And in theory, that all works. In practice, we haven't done it yet. Okay. A lot of this work is with my students, so you can see the papers on my web pages, and you can see whom I'm working with. Okay, so then we have a way to analyze parallel complexity of programs. So for example, we can analyze the fact that this queue is quite efficient as far as parallel complexity is concerned, because we can process requests with only delay of 2 units of time, okay, between 2 consecutive requests. So it's very good parallel-wise. And we do that by adding on top of what we have here temporal logic. And giving, so what we get is a linear time, linear logic, okay? And if you give that an operational semantics and you work out things the right way, then you get a very nice formulation, and you can characterize the running time of these programs, at least in an abstract sense. And Siva, who's sitting back there somewhere, yeah, back there, he's working with some new aspect of this that's not yet been published, okay? And then we also worked out sequential complexity on top of that. And for that, we need what I call an ergometric logic. And essentially what we do is we cast into a type system or a logic the amount of work that a given program has to do. Okay. Actually, I should put logic in quotes here because I'm not really sure yet if it's a logic. Okay. It's a type system, and that works, but I'm not sure that it makes sense without the programs. Because if you don't run anything, how much does it cost? It's not obvious right now. But anyway, so you can measure the sequential and the parallel complexity of your code, okay, using these things. Now, if you actually try to grow a system of session types bottom up, not using this kind of logically based approach, I would venture to say this would be a pretty hopeless enterprise. But logic are constructed so that the meanings of the connectors are defined independently from each other. Right? Every connective was defined by left and right rules. So then we can add on top of what we already have now the rules for a next time operator or for a future time operator or whatever. And hopefully if we do this the right way, these things actually fit together, okay, because we're working in a logic. So these two things succeeded pretty much because of that. Then we have added index types, and then a very important development, I think, is to actually add also shared resources, not just shared memory. And that was a paper from ICFP 2017. This was ICFP 2018, this was LIX 2018, and this was ICFP 2017. And shared resources are very important, and actually what happens is that you have another layer that it has the same typing rules essentially as this one, but the down arrow here is acquiring a shared resource, and the up arrow is releasing a shared resource, okay? And then we have brought a bunch of code on that, for example, like the dining philosophers example, or the cigarette smokers problem. And I'm currently in the middle of implementing the Raft distributed consensus protocol using this language. And so far I haven't hit any obstacles. I'm just not finished because I actually need to prepare lectures. Okay. The final thing we're doing is when you do recursive, well, it's not the final thing, but the last thing I wanted to mention is that when you add arbitrary recursion, you lose the strong connection because you can no longer read the type system as a logic. But Farzaneh, who is also back there, and I are looking at recovering a logical interpretation. And I mentioned this in the previous lecture. By not having arbitrary recursive types and arbitrary recursive programs, but having least and greatest fixed points, and circular proofs, and make sure that these all fit together. And if you do that, then you can make some stronger guarantees about, let's say that your programs are reactive. So in this language, if I send this queue a message NQ, I could write a program that never responds because I could be in a stupid recursive loop without doing anything. And the type system does not prevent that because recursion is not restricted. In the system that Farzaneh and I are working on, that program would be rejected as being not terminating or not productive or not reactive. We haven't found the right term yet. But anyway, it's not valid, and so you can't write this program. So whenever you do that, you give something up because certain programs that you want to write no longer works, like the Turing machine. But if it does check, then you have some very strong guarantees. In particular, if you have a process that doesn't use anything and just has, and you are the only client of it, and it's supposed to send you a message, it will do so definitely, okay, which is a very nice guarantee to have. And I think I've shown you enough here that you should be able to read any of these papers and drafts that are on my webpage to learn more about it, ask me questions or whatever, but I won't be able to give you first-hand account of them. Okay. All right, any more questions? All right. I guess the lecture was, yes?
Would you mind noting which conferences you said you were talking about? I couldn't quite catch those.
Yeah, okay, so the parallel complexity was LIX 2018. The sequential, no wait, sorry. I always get these two mixed up. This was ICFP 18, and this was LIX 18. This was a shared memory semantics as a draft, hasn't published yet. The shared resources was ICFP 2017. And the recovering the logical interpretation is in draft form. Okay, that's where we are. Like I said, all these papers are available on my webpage if you want to read any further. Yeah?
What implementation can we use to play with that?
That's a very good question. There's an old implementation of a language called SIL in which you were able to write this. But I haven't used it for like 2 years, so I don't think it compiles anymore. It was written by a student of mine, and we're in the process of now rewriting a new implementation that's not there yet. On the other hand, we have an implementation of the subsingleton fragment of this logic. And that I'm prepared to share if people are interested. And I'll put it in a Bitbucket repository. And that actually implements both the temporal logic and the ergometric logic. It doesn't implement the shared resources. It does implement the least and greatest fixed points. So it implements at least 3 of these 5 things, but on the restricted form of the subsingleton logic. So you won't be able to write the Q program, but you will be able to write these other programs that we wrote earlier. Okay, any more questions? All right, sorry to keep you over time. Thank you.